Dosember 2023. I am DOS Logo. This is the boot screen of DOS. Windows 98 in this case. Look at how many colors are displayed compared to what it could have looked like. I believe that we can fix this if we reprogram the entire thing, but first we need to understand why it is the way it is, why it's so good. Stay tuned.
So in this video we will create and program a 16 million color boot screen for Windows 95 using hardware from the time era. Being able to show graphics without having limited colors, banding or dither patterns will truly show off the real design of that Windows 95 logo and clouds that everyone remembers. Of course, this is not limited to just Windows 95. It can be shown in greater effect using Windows 98's boot screen. It's not even limited to that. You can use it for MS-DOS 6.22 or even IBM PC DOS 7.1. It is completely compatible with MS-DOS because it really is the boot screen of MS-DOS. In order to replace the original boot screen with our own, we need to obey the same rules that it had. And that is to not interfere with any existing DOS applications or device drivers, and there are a lot of those since 1981. And to make things worse, the boot screen must not interfere with any Windows programs or Windows 32-bit device drivers as well. It needs to be cancelable by pressing the escape hotkey, thus showing the boot process text that must be preserved and updated while the boot screen was active. Being able to self-terminate when keyboard input is required by the user or when a graphics mode switch is in effect. Being able to animate a bar at the bottom of the screen to show that the boot process hasn't been hung. Simple enough, we can do it. To understand the original boot screen, we will create an MS-DOS exe that will dump all video memory areas to the disk so we can examine it. We will do this while the boot screen is active. The boot screen is self-terminating if any keyboard input is checked for, so we will use no such thing. To show that we actually dump video memory, I will sound the PC speaker with a specific tone for each video memory segment. That's what these functions are for right here. And the import and output functions we're calling will be intrinsic functions because I don't want to include conio.h. That's as simple as that. We will save segments and size. The segments will be B1000 hex for monochrome text mode, and the size for that one is 32 kilobytes. And we have color text mode at B800 hex, 32 kilobyte size as well. And then lastly, the graphics at A1000 hex, 64 kilobyte of size. Here we will put a little delay for the PC speaker to sound, and we will take a byte from video memory. This looks like C to me. It doesn't, but it's really. And we'll write it to disk. And then finish up the main functions. File name, segment, and size. And that's done. The most important thing is the command line switch OI to generate intrinsic functions. After booting the computer into safe mode command prompt only, editing CONFIG.SYS with an install command to execute our exe at the earliest time allowed in the boot process. Then running the DOS debug command, rebooting into the master boot record with an int 19h instruction. At the boot screen, we will hear the 3 tones playing off the PC speaker. 3 video memory segments have been dumped to disk successfully, so we can analyze them. So looking into the contents of the saved files, the B1000 hex, the monochrome text mode, is just full of bytes filled with FFs. The B800 hex file has the text mode characters and attributes that were active under the boot screen at the time the memory was dumped. At the graphics mode address A1000 hex, there is nothing more than FFs again, this time spanning across the entire 64 kilo segment that the CPU can access. No boot screen graphics to be found. We will do the same thing again, but in monochrome text mode, booting the computer into safe mode command prompt only, running instructions from the DOS debug command to set the video mode 7H, the monochrome text mode, then booting into the master boot record using int19H. The familiar 3 tones will be played again to tell us that the video memory has been dumped to disk. Looking into the contents of those files will show the same thing as before, only the text mode and attributes will be in the monochrome B1000 hex instead of B800 hex, where we can only see FFs again. The graphics mode A1000 hex is still empty of graphics, just having FFs across the entire addressable 64K segment. Lastly, we will do something a little bit more hacky. We will intercept the Windows boot process and spawn a command prompt just before the Windows kernel has started. We're technically in protected mode, executing in virtual 86 mode in the system virtual machine. This allows us to execute kernel 386.exe ourselves. Windows desktop will then show up. Once we exit Windows to shut down the computer, that same command prompt will be there to greet us, but user.exe has now drawn the end screen that we can dump with the exe we created. And yet again you hear those 3 familiar tones from the PC speaker telling us that we have successfully saved the 3 video memory locations to disk. Now this gets a little bit more interesting. When looking into the dumped files, B1000 hex and B800 hex both have text mode characters and attributes in them, but they are basically empty. This is the virtual machine manager's protected mode shenanigans going on. We don't care about those. Instead, we're looking into the segment A1000 hex, where we will now finally find graphics. By looking down at 8000 hex, which is A800 hex, we can finally see some of the graphics we were looking for. It is not all of the graphics. It is exactly 1/4 of the pixels that are visible on the screen. This is the so-called 4 planes graphics that the VGA hardware supports. It's an undocumented video mode that somehow works on every single VGA hardware out there. You might have heard it before. It is one variant of the so-called Mode X used by popular games at the time, both for MS-DOS but also within Windows using Direct Draw, but only when specifically telling it to use it. The 4 planes each accesses 64K of video memory, so total of 256K can be used for graphics, not counting the resolution supported by the monitors, and the speed of the VGA adapter. This is why VGA has 256K of video memory. The 320 by 400 video mode takes exactly 128 kilobytes, which is half of the VGA's video memory. So the reason to keep the boot screen graphics at a higher location of video memory is directly linked to the idea of having text mode at a lower location where it is directly accessible by the CPU. After all, if the video memory is mapped into B800 hex for only 32K, the other 32K with the graphics will be hidden from any programs, and no one would ever think about reprogramming the VGA's registers to change what is being visible to them and what is actually being displayed on the screen. How can they even know? So the boot screen gets to be drawn an invisible page. That is not completely true. While the boot screen is being drawn, time to change which plane is writable takes time. And that does slow down the initial display of the graphics to a crawl. This is where yet another trick is being utilized. The VGA registers allow for the monitor to be blanked, to hide what is being displayed. Blanking is not the same as turning the monitor off, but rather reroute what is being displayed to just display something that seems like the color black. It is enough to not make the boot screen graphics look slow while it's being drawn, but nevertheless to keep the flow of the boot process looking as tidy as possible. So our 60 million color boot screen can't do the same trick with the blanking of the monitor. So how did I make it seem like the entire graphics was shown in one go? VESA mode doesn't allow any modification to the VGA registers by simply mapping them out of IO space. A few registers might be there, but if they are not, things can really go bad if looking for them. But VESA does provide something very exciting. All, and I mean absolutely all, of the video memory is accessible to us, as long as we are in a valid VESA mode. That means all of the pixels and text, everything. So it is then possible to set a 256 color VESA video mode and then slowly draw the 60 million color pixels while the screen is totally black. And then when the screen is fully drawn, the VESA video mode is switched into 16 million colors and the graphics will pop up in one instant. Yes, you heard that right. Totally black doesn't mean blank. Like monitor being blanked, 256 colors mean it has a palette, so all we need to do is clear all of the palette entries to the color of black, that is, zero them all out. Since video memory has no actual state of being in either palette or direct color modes, or in text mode, whatever is drawn in the 256 colors video mode might be completely bonkers, but when switched into the correct video mode with 16 million colors, that same video memory data will make sense, and everything will look just fine. That is just one of the tricks that we can use by interpreting the VESA standard in a smart way. Take advantage of everything as long as it is being within reason. Text mode is treated the same way. As long as switching between graphics mode and text mode, no video memory must be cleared. It is then all up to us to find where the text mode lies within the video memory and how to read the internal format used by the specific display adapter. And oh boy, does that get complicated. But again, things start working out once you figure out how to exploit the VESA standard. I really do want to show how I managed to do all this. Post in the comments if you're interested. So now let's look at the final product. But first, we do need to draw the actual boot screen logo. And why not just do a perfect Windows 95 logo and clouds in 16 million colors? Just to show what it would look like if we use 256 colors, because VESA supports 256 colors as well. It wouldn't look very good and you would have to use dithered patterns to smooth out the colors. The other part is if we would have used 64K colors, so-called high color, we would be able to see each gradient step between colors, and that's not good enough either. So have a look at what happens when we use 16 million colors. You can no longer see the actual color steps. There is absolutely no limits here. We see everything the way we want it. The most complicated part of the 16 million color boot screen was the fake text mode management. As long as the programs are full to use the BIOS for text output, we can intercept all the needed functions required to display text correctly, including text scrolling, clearing of the screen, text color, etc. However, we don't have access to the VGA registers in VESA mode, so we can't change any hardware states like the original boot screen does. So we must keep track of much more things, and thus more code is needed to do the same thing as the original did. I really would like to show all the code and what it does and why it was needed and how many computers were actually needed to understand the entire process of writing this thing. So post in the comments if you want a guided tour through the assembler code, and that will become the future video on this channel. I really recommend it as the code has areas that rewrite itself to be faster. As an example, calculating where the text would end up on the screen requires multiplying the offset by certain steps. These steps could be calculated each time the text character is outputted to the screen. However, That approach is slow. Because we are in real mode, we can just update the machine code with the already solved calculations, and the code itself will just know the answer depending on what video mode was used at the time the boot screen took over. That includes the higher resolution text modes that VESA provides, so we support those special text modes that the original boot screen never did. The animation of the 60 million color boot screen is done through caching all required banks and offsets needed to quickly copy pixels from one side of the moving bar to the other side. Doing this takes much more CPU time than palette cycling, but we can't do palette cycling in 16 million colors. So we have to do some real optimized hand-coded pixel manipulating operations. We also have to count for different implementations of hardware, such as if 16 million is represented as 24-bit BGR, blue, green, red channels, or 32-bit BGRX, blue, green, red, where X is padding, as well as frame buffer pitch. The frame buffer pitch can be wider than the visible screen, which affects the moving bar. This boot screen is easily installed on your DOS machine by copying dlogo16m.sys onto your boot root directory, along with the logo9x.bmp of your choice. Then edit your config.sys to add the line device equals dlogo16m.sys and make sure it is added at the top so that it is loaded first. If you don't want the original boot screen to show up for that split second, io.sys is spending time doing the boot warn and pre-configuration manager stuff, edit your ms-dos.sys file to add the line logo equals 0 under the bracket options. But in case you don't care about the original showing up, don't worry, as the 60 million color one will nicely close it down in an official manner before showing itself. The logo9x.bmp file is a completely standard bitmap file, saved as a 24-bit 640 by 480 image. It has never been easier to make graphics like this, as you don't need to care about palettes or weird aspect ratios. What you draw is what will end up on the screen. So find the download link to the device driver in the video description, as well as 2 included boot screen logo bitmap files. Choose the one you like the most or draw one yourself. And again, if you're interested in the source code and how to build this thing, we can go through that in the next video. I'm kinda running out of December time. Thank you for watching this video. Hope to see you again. Bye bye for now.